We're going to take a look at some real-world models of sinusoidal functions. So the first one is a water wheel here, and as it rotates, it's rotating 6 revolutions per minute. 2 seconds after you start a stopwatch, point P here on the rim of the wheel is at its greatest height, which is 13 feet. That's 13 feet above the water. The center of the wheel is 6 feet above the surface. So it's got a radius of 7, so it sits, the bottom there sits 1 foot below the surface, so the center is 1 foot above, or 6 feet above the surface. First, we're going to sketch a graph as a sinusoidal function of t, which is time in seconds, after starting the stopwatch. So some important things from this paragraph. 6 revolutions per minute sounds important. 2 seconds after starting a stopwatch sounds important. When it's at its greatest height is important, and that height being 13 feet above the surface of the water, and the center being 6 feet above the surface is important. Okay? If the center is 6 feet above the surface, that means your sinusoidal axis is at 6. Okay, so we've got sinusoidal axis at 6. We have a radius of 7. That's going to be our amplitude. That means that our maximum is 7 above that, 13 feet. And it says that here the greatest height is 13 feet. 13 minus 6 happens to be 7, the radius of the water wheel. Which means it also goes 7 feet below this axis. And 6 minus 7 is -1, so it goes 1 foot below the surface of the water. We know that it's at a maximum of 13 feet 2 seconds after we start our stopwatch. 6 revolutions per minute, that is the frequency. And the frequency is the reciprocal of the period. Okay, so the frequency is 6 revolutions per minute. Okay, so we need to turn that into per second because we're in seconds here. Okay, so every minute is 60 seconds, so that's 6 revolutions per 60 seconds. Which is 1 revolution every 10 seconds. The period is the reciprocal of that, so it would be 10 seconds per revolution. So that means 10 seconds after this point, we are going to have finished a cycle. So we're here at the maximum, it goes down to a minimum, and back up to the maximum 10 seconds later at 12 seconds. Assuming d is a sinusoidal function of t, write a particular equation and then confirm it by graphing. In order to write the equation, we need s, a, d, and b. Our sinusoidal axis is 6. Our amplitude is 7. Our displacement, the first time we know that we're at a maximum or a minimum, we could use this minimum here 6 seconds later at 8. We'll use the first time we know we're at a maximum, and that is at 2. And b is 2 pi over the period, 2 pi over 10, which simplifies to pi over 5. So our equation, d equals sinusoidal axis, and then we're starting at the top, that's cosine if we're at the top or the bottom, and since we're starting at a displacement of 2, the top means plus cosine. 7 is the amplitude, cosine, so plus 7 cosine. Then b, pi over 5, times Our displacement is 2 to the right, which means minus 2. And for my variable here, I'm going to use this t for time. Okay? Then we're going to graph it here in the calculator. In order to graph a sine wave, first I need my mode to be radians. So 6 plus 7 cosine, and it opens up parentheses for me, pi over 5. And then I'm going to open up another set of parentheses for t minus 2, and I'm just going to put an x. And I'm going to close both sets of parentheses. And I'm going to go to my window. I don't need anything left of 0 seconds, so for my x minimum, I'll put 0. My x maximum, it goes up to 13. I'll go a little bit above that, so I'll go to 15. Scale of 1. My y minimum, it only goes down to negative 1. I'll go a little bit below that. Negative 3. And I misspoke here for the x maximum. I went with the y maximum. For x maximum, I go up to 12. My 15 is still okay. I guess it goes a little past that 12. My y maximum, it goes up to 13, so I'm going to go a little past that, up to 15. And graph. But we didn't graph this whole thing, but if we did, that part was missing, and we didn't continue down here. This part right here tells us enough of the story to answer the rest of the questions here. How high above or below the water surface will point P be at time equals 17.5 seconds? And at that time, will it be going up or down? So all I need to do is trace 17.5 seconds. Now that actually tells me I'm going to have to probably increase my window a little bit because I've got an error. So we'll go back to the graph. And actually we'll go back to the window. And our x max, we need to go past that 17.5 seconds, so we'll go to 18 seconds. And then we'll trace 17.5. And we're at negative 0.657 feet. And then is it going up or down? It's past this minimum here, so it looks like it's on its way up. And the last question here, at what time was point P first emerging from the water? Okay, so on our graph, the first time it emerged from the water was right there. So we'll trace, or actually we'll calculate We're going to calculate a 0, so when it's crossing the x-axis. And we want that 0 to be where it's first emerging from the water. So left boundary there, right boundary there. And we're at 7.86 seconds. So we're first emerging from the water at 7.86 seconds, which actually highlights a mistake that I made up here. I said here at this minimum we were at 8, but we're not at 8. Halfway between 2 and 12, it is not 8, it's 7. So we were actually at our minimum at 7 and emerging from the water at 7.86 seconds. A fox population problem. Naturalists find that the population of some kinds of predatory animals vary periodically with time. Assume that the fox population in a certain forest varies sinusoidally, probably rises when there's more prey and goes down when there's less prey, when they've eaten it all, and then they move on. Records started being kept at a time of 0 years. So whenever they started keeping records, we're calling that 0 years. A minimum number of foxes at 200, so that's my minimum, appeared when time was 2.9 years. The next maximum of 800 foxes occurred at 5.1 years. So we know that the maximum is 800 foxes, and the minimum is 200 foxes. Okay? Halfway between those is the sinusoidal axis. So 800 plus 200 divided by 2, so the average of the max and the min is 500. So the sinusoidal axis is 500 foxes. We know that we were at a minimum of 200 foxes at 2.9 years. And we were at a maximum of 800 foxes at 5.1 years. So a little portion of the graph would look like that. That's all we're really going to need in order to get all the information we're going to need from this graph. Okay, so an equation. S, A, D, and B. The sinusoidal axis is 500. The amplitude, it goes 300 above and 300 below the sinusoidal axis. The displacement, the first minimum we know is 2.9. We could use that, and we're going to have negative cosine, or we could use 5.1 and have positive cosine. B is 2 pi over the period. Now this right here represents a half of a cycle. Okay, so this right here is a half a cycle, which makes this really half of a period. We have to figure out what it takes to get there to make a whole period. Okay, so 5.1 minus 2.9 will give us that half period, and that is 2.2. If you double that, you're going to get 4.4. So the period is 4.4 years to go from a minimum to a maximum and back. So B is 2 pi over 4.4. Now if we multiply top and bottom here by 10, we'll get 20 pi over 44. And 4 goes into both of these 5 times and 11. So B is 5 pi over 11. So our total number of foxes is 500 plus 300. Actually, that should be minus 300 because I did start at the bottom. So it's minus 300 cosine. B, 5 pi over 11, times time, and then it's displaced 2.9 years, minus 2.9. So I'm going to clear out my equation and put in 500 minus 300 cosine. It opens up parentheses for me. 5 pi over 11. Another set of parentheses. Time minus 2.9. Close both parentheses. And for my window, for x's, I could go from 0 to say 7 years. Well, this one's 10 at least, so I'm going to go 0 to 10 years. For the y's, how about 0 to 800? But that's a big range, so let's count by 20s. So a scale of 20 and graph. So we want a prediction of the fox population at 7, 8, 9, and 10 years. So trace 7, or about 227 foxes. 8 years, 337.8, so about 338 foxes. 9 years, about 727 foxes. And 10 years, about 727 foxes. So at that point, it has gone up to the maximum and back in that year between 9 and 10. Foxes are endangered when their population is below 300. Between what two non-negative values of t were they endangered? So we want to know when the foxes were below 300. So if we trace, and we'll go back toward the beginning. So here we are early on in our study. When did they go below 300? Looks like right about 2.3 years. And when did they come back out of endangerment? When they crossed back over 300. Looks like about 3.5 years. And on this graph, we're going to see another place where they were endangered, another time. Looks like 6.8 years. And then they came back out of endangerment. About 7.97, right about 8 years.